Hello and welcome to the Simulated Autonomous Vehicle project made by Binyamin Brion, Andrew Hall, and Frank Yu. Many leaders in industry and science have pinned autonomous vehicles as the future of transportation. It is for this reason that the group chose this project. Developing an autonomous vehicle can be prohibitively expensive. For this reason, the system was developed in a simulated environment with the goal that it should be able to be easily translated to a real car in the future. This is the third iteration of the project. Two previous groups had worked on the autonomous vehicle as well, and had developed a system that had some of the functionality required for an autonomous vehicle, but was not reliable enough to be considered safe. The goal of this year was to have the car be able to navigate safely in a neighborhood environment. This entails avoiding parked cars, listening to stop signs, and also detecting lane boundaries and properly following them. AirSim was the simulation engine used for development. AirSim is specifically designed for the development of autonomous vehicles, and it comes with a variety of different environments, including a city environment, a coastal environment, and most importantly, a neighborhood environment, which fit with the team's goals for development. The team used ROS, which is a commonly used framework for robotics applications, to develop the system in. This system uses a publisher-subscriber structure, meaning that each separate system is able to talk to each other only through specific channels. This allowed for a more modular development environment, and also ensures that in the future, these systems should be able to be plugged into a real car quite easily. The system was constructed in 6 separate subsystems. Mapping and navigation provides the baseline output the rest of the system will follow. We do this by using our own custom mapping tool in order to allow us to create maps, and we use algorithms in order to navigate the breadcrumbs. The cruise control subsystem is used to modulate the throttle in order to maintain a constant speed. It does this by using a PID controller, which uses feedback from the car in order to maintain this constant speed. The lane keep assist subsystem tries to detect the lane boundaries that the car is in. It does this by using a variety of algorithmic computer vision methods, like edge detection and color thresholding, to try to then fit lines to those detections and then send them all to the other subsystems. The camera object detection subsystem uses a machine learning model to detect a variety of objects on the road. The two of interest for this group were cars and stop signs. LiDAR object detection instead uses the LiDAR sensor and data from a 3D space in order to detect objects. It sorts through the data provided by the LiDAR and creates bounding boxes for detections. Finally, the output from all the different subsystems is filtered into central control. This subsystem makes a decision based on the outputs of all the other subsystems. This can range from following the path normally provided by navigation, to avoiding an obstacle detected by either camera or LiDAR object detection, and even stopping for stop signs. The group is quite happy with the work done on this project, and hope that future groups can build on what was done in this iteration and come up with an even safer vehicle.